Hi, welcome to Module 3 on electricity and magnetism. Now, way back at the start of this subject, I again mentioned that physics was about the world around us. And indeed, the things we've covered so far, motion and sound and waves, they're definitely things we can look around and experience every day. But if we look around at our modern technological world, there's actually one aspect of the universe that seems to be being used more than any other, and that's electricity. In terms of transport, lighting, heating, cooking, communication, so much of what we do and how we interact with the world is based upon electricity. So in this module, we're going to be dealing with a whole range of aspects to do with electricity and its closely associated phenomenon, magnetism. Now, if we look at the universe very closely, we soon discover there's some property of the universe that's a little bit like mass giving us a gravitational force, and it's a property that we call electric charge. It also gives rise to a force, as we'll see very shortly. Now, electric charge, unlike mass, comes along in two kinds. There are positive charges and there are negative charges. In fact, those labels, positive and negative, were given to the electric phenomenon by the very famous American inventor and scientist Benjamin Franklin. And he chose very well, because just like positive and negative numbers can cancel out, positive and negative charges can do the same thing. In fact, it turns out that everything in the universe is essentially composed of positive and negative charges, but in essentially equal amounts. So for example, yourself, you are composed of a whole bunch of electric charges. You don't feel terribly strong electric forces most of the time because your positive and negative charges are exactly balanced. Sometimes you can upset that balance. For example, if you rub certain shoes as you walk along the carpet, or if you pull off a nylon sweater quite quickly, you might experience that notion of building up a charge. In the case of rubbing your shoes, if you touch a door handle or someone else, you might see a small electric spark. In the case of the sweater, you might find the sweater clings to you or maybe even makes your hair fly away a little bit. What you're experiencing there is in fact the electric force between charged objects. Now, another famous scientist by the name of Coulomb came along and analysed this idea very, very closely. And he came up with a nice description of how that force depended upon the various properties of the system. So if we look now and see two charges, I've drawn them as spheres here, and I've labelled them Q1 and Q2. In fact, Q is the symbol that we use for electric charge. So charge, we will use the symbol Q, and we measure it in units of coulombs, which is a C there, named after the scientist Coulomb. In fact, the coulomb's a very big unit. Often we'll have things like millicoulombs or microcoulombs because it turns out not very often do you have as much charge as 1 coulomb. Anyway, when Coulomb looked at this, he discovered that the force between these two charges was always along a line between the two charges, directly between them there. And of course, there was two kinds of systems he could have. He could have that the charges were both the same sign, that is, two positive charges or two negative charges. If that was the case, then the charges actually repelled each other. That one would get a force in that direction, and that one would get a force in that direction. The other example was if one was a positive charge and the other was a negative charge. Then the force was still along the line in between them, but now it was a force of attraction. And often we will remember this by the phrase that like charges repel, opposite charges attract. And he did a bit more than just discover that. He figured out how did the size of the force depend upon things like the size of the charge. It turns out that the larger each of the charges were, the larger the force was. What about the distance between them? Imagine these two charges are separated by a distance that I'm going to call r here. It turned out that if you made them twice as far apart, you only got 1/4 of the force. And it seemed like the force depends upon the inverse square of the separation of the charges. So we can write down what we call Coulomb's law, that the force between these two charges is going to be proportional to the size of each of the charges, Q1 multiplied by Q2, and it's going to be divided by the square of the distance between the two of them. Now, to make all of these units work out, coulombs and meters, to end up with a force in newtons, there's a symbol in there, a K, and that K is just a constant that depends upon the units that we're using. We're not going to worry too much about the value for that for the moment. More importantly for us is the fact that Coulomb's law tells us if we increase the size of the charge, we increase the size of the force. If we increase the separation between the charges, we reduce the size of the force. Now, what we're going to be doing in the next topic is analyse that force, particularly in terms of the energy that's available. Remember back in motion when we discussed how we can talk about forces in terms of work done? That's exactly what we're going to do, and actually come up with the notion of an electric potential energy. But before that, I'll again encourage you to get onto the discussion forums and maybe talk about some ideas you might already have about electricity. You might have some examples of situations where you've seen things build up a static electric charge. And another idea to think about and maybe discuss is if you pull off some nylon sweater and it seems to be sticking to you, is there any way you can tell what the charge on the sweater must be and what the charge on you must be?